All right, let's do a problem. So that first one we did, uber minor, right? No big deal. Well, let's do another simple one, but you're going to see that as soon as we now have r is equal to a function of theta, we're going to look at this fancy thing here. We messed around with these before, didn't we? In our last section, r equals 1 plus sine of theta. Cool. Cool. Yeah. It's just a little heart-looking thing. So I wrote in just a sketch a graph, but this is just something to kind of get an idea. I'm like, all right, well, there's a sine, so I know it's symmetric about y, and it's one of them cardioid things, right? It's going to look, jeez, I'm so terrible at drawing. It's going to look a little something like this. And I'm going to stick pretty simple with y'all. We're going to graph cardioids, and we're going to graph rose curves. Sometimes the cardioids can have inner loops, but we'll get to that when we get to that. So for right now, I think that's a pretty good little sketch. It's the same thing as what we have done in the past. So having an idea as to kind of what it looks like, it doesn't need to be perfect either. Just an idea where it's like, brother, thing's symmetric about y. So right off the bat, you can see that you have horizontal asymptotes, or what am I saying, horizontal asymptotes? Horizontal tangent lines, sorry about that, at pi over 2. Looks like we have some down on the cheek, down at the bottom, right? We got something where it's flat. We got some vertical stuff here. I don't know, maybe that's at pi, maybe that's at 0, because I just sketched a graph. I don't know where the hell it's at. Don't trust anything I draw. And we don't actually have to sketch a graph, but seeing that there's some sort of issue, or seeing where something should pop up, is kind of nice. We also see that we have this sharp edge right in here in the... at 3 pi over 2, let's just say that. I want to call it the crack. Looks like there's some sort of issue. Looks like there's some sort of sharp edge that might be going on there. But I'm going to stop talking on that because, well, I'm 12. I might look 60, but I act about 12. All right, moving on. We're going to have to go find the derivative. Not that big of a deal, so let's make sure to pop it up first few times, right? Keep the formula near you. Try and find ways to get it memorized up. So we're going to say our dy dx is indeed equal to. And remember that this is a function of theta. So while it might give it to you as r is equal to something, think that's your f. So I can't spend too much time because this video is going to take about 15 minutes to do this problem. So I got to start running through it. So let's maybe just write it down now. The derivative is going to be just cosine. So the only two places where we have a derivative are right at the beginning. So we just write in cosine and cosine. And now it's just plugging things in where they go. That says sine. So that is just sine. It's just sine. You have no choice. Down below it says cosine. These don't change. The only thing that changes in this formula is your f primes of thetas and your f of thetas. Those cosines and sines are just there. So next we have to put in, we have a plus up top, we have a minus down below. We got to put in our f of theta, or r, which is 1 plus sine of theta. And 1 plus sine of theta. And then at the very end, we just have cosine and sine. And I guess for right now, we could kind of just leave that alone because we're going to need to do a lot of fancy footwork here. So this was our second part, but I got to mess with it a little bit. Got to clean it up. Cosine times sine. I always call it sine times cosine. Stay consistent if you can. Bring all that stuff through and we get plus cosine, plus sine cosine. Yeah. Find a way. Either write cosine before sine or sine before cosine. That way you keep a good, consistent way of doing things. Because if you're like myself, where I make lots of silly mistakes, you want to find anything you can do to help your brain out. So we have sine times 1, but that's negative, so that's negative sine. We have sine times sine, but there's still that negative, so that's negative sine squared. Let's go one more step with the cleanup. And looks like we have a sine cosine and a sine cosine, so I believe we have 2 sine cosines plus cosine all over. Don't call that cosine's double angle. Please don't call that cosine's double angle. I'm just going to leave that there for now, knowing that there's going to be a lot more work that needs to be done here in just a little bit. All right. Good enough. MyLab's going to take this, right? You'd be super stoked to get your 0.00001% of your overall grade by getting this punched in right, huh? Make sure to get that thing that doesn't even account for rounding. Make sure to get that. Don't understand. Just make sure that you get it so you can get those points that don't matter so you can mess up. Sorry, I got to stop being sarcastic. All right, make sure that we pay attention to what we're doing here. It's not about the homework. The homework is there to help us get better. Cool. Now we want to find where the tangent lines are horizontal and where they're vertical. Well, we have some suspects already. I'm kind of just thinking about this thing. Like, all right, I got an idea. But the way we're going to find something to... Where would it equal 0? That's the numerator. You want to find where horizontal. That's where f prime of theta is equal to 0. You want vertical. That's where f prime of theta is undefined. Possibly. Possibly. I don't know, suspects. So the only way we're going to make something equal 0 is by the gosh darn numerator. The denominator doesn't make something equal 0. I mean, unless there's some limits, unless we found that something up top and something down below equals 0, then we'd have the L'Hopital situation. So what we're going to do is we're going to take this. We want to find our horizontals. So we're going to take our numerator and set it equal to 0. Which means we got to do a little factoring. We got to go back to trigonometry. You remember doing trig equations, don't you? Therefore, so we factored it. Now we can use the zero product principle. So cosine of theta equals 0. 2 sine of theta plus 1 equals 0. So I'm not going to show my work on that. Sine of theta equals -1/2. Therefore, well, between 0 and 2 pi, that's all the only place we're looking, just between 0 and 2 pi. We're going to say theta equals 0 from cosine. Well, we all know this. That's just odd multiples of pi over 2. So pi over 2 and 3 pi over 2. And then sine of theta equals -1/2. We got to find that like reference angle. We'd be like, well, sine of pi over 6 would be +1/2. Now we got to think about the quadrants. So we'd be like, third, right? Negative down here. Down there, third and fourth, so that'd be what, 7 pi over 6 and 11 pi over 6. And if this isn't making sense to you about where I'm getting these values, it's coming from a class 1, 2, at least 3 classes previous. So we got to work on that stuff. We got to make certain that we know these values, or we can't do something new. So when we look at this, we're like, hey, we found out that it pi over 2. Hey, that makes sense. We found that 7 pi over 6. All right, that makes sense. 11 pi over 6. Yeah, that makes sense. But 3 pi over 2? That doesn't make any sense. These are suspects. So I'm curious about this one right now. That doesn't seem right. But you don't have to even look at the graph. There will be something in the next part that's going to tell you that there's something wrong with 3 pi over 2. So I'm very convinced pi over 2 works, 7 pi over 6 works, and 11 pi over 6 works for horizontals. Now let's do the vertical. Vertical, we're going to set the numerator equal to 0. Or numerator, gosh darn it. The denominator. Gosh dang. So we get cosine squared minus sine squared. Now, good luck with this, solving it as it sits. The issue we have is we have 2 different frickin' words. We got cosine and we got sines. Now, what's telling us what to change it into is there is a sine without a square. You can't change a sine without a square, and I just want one frickin' picture. I just want to deal with sines, or I just want to deal with cosines. The thing is, there's that sine right there is determining that I got to change that cosine squared into something. I got to change that into sines. Because I can't change just sine of theta. I sure as heck can change sine squared. So can you. And we can change a cosine squared to a 1 minus sine squared. Now at least we have the same frickin' picture. We didn't need a different picture back here because it factored super nicely. And we could use the zero product principle. But down here, oh hell no, that's not going to work out nicely. So let's clean it up and let's put that in descending order. Looks like we have two of those sine squareds. Negative, of course. Oops, did this one. And then minus sine. Let's put this in descending order because it is a quadratic. It's just with words and then, oh man. Well, let's do this next step. Don't get in this habit of, you're doing it at home. You're like, oh, I'll just factor online. Yeah, great practice. Let's multiply by -1 everywhere. There we go. Now that might be factorable. And if it's been a while, just let sine equal y. Or you can let it equal x. I can't. I'm a teacher. It's 2y squared plus y minus 1. So what is that? I'm not doing any weird uncle tricks here. There's nothing to do. So that one needs to be positive and that one needs to be negative. Yep, there it is. That'll work. So we can put it back in, and instead of writing it as y's, we're going to write it as sine. So you get 2 sine of theta minus 1 and sine of theta plus 1. Now it's factored. Now we can solve. It's like, dang, I should have paid more attention in that trig class. So 2 sine of theta minus 1, we said equal to 0, and sine of theta plus 1, we said equal to 0. Do our work. Sine of theta is equal to 1/2. Sine of theta is equal to -1. Therefore, we find out that theta is equal to pi over 6 and 5 pi over 6. That makes sense from the graph that we showed before. I thought it might have been 0 and pi, but no, I guess it was wrong. Then down here, if you just use an inverse, you're going to find negative pi over 2. Let's not use negative pi over 2. Let's use 3 pi over 2, because we want to deal with stuff between 0 and 2 pi. You'll see it over and over and over. So using inverses with negative numbers is not going to work out well. We got to know these values. So there it is. Vertical tangent lines at theta is equal to pi over 6 and 5 pi over 6. But wait a second. We got this silly 3 pi over 2. Dang it. Dang it. We found that it's also equal to 0. We found the numerator that equals 0 and the denominator equals 0. Wait a second, isn't that something called L'Hopital's? So let's take our derivative one more time and let's take our factored versions. Our factored versions of the numerator and the denominator, let's set those things up with a cosine of theta times 2 sine of theta plus 1 all over 2 sine of theta minus 1 times just sine of theta plus 1. So we factored that thing on up, and it's like, shoot, when we plug in 3 pi over 2, we get 0 over 0. So let's take a look and see what's going on. And we're actually going to say, let's take the limit as theta goes to 3 pi over 2, but we're actually going to say it comes from the left. Because did you know that when you go around in a circle, in the positive direction we go to here, then if we're coming to 3 pi over 2, we're popping in from the left. That's right. Oh my goodness. We're coming up on 15 minutes. We're getting there. Of cosine of theta times 2 sine of theta plus 1 all over 2 sine of theta minus 1 sine of theta plus 1. Why am I writing so weird? I'd rather do this in 2 pieces. I don't want to deal with all those frickin' products. I don't want to deal with all these frickin' products. Actually, I'd rather spin this thing around. I'm like, wait a second, I don't want to do a bunch of frickin' products. Let's write it as 2 sine of theta plus 1 over here and cosine of theta over here. And then we can use our limit laws. Instead of having to like bring it all together, it's going to turn disgusting. I don't want to deal with all that crap. So we can actually just write it this way. And why am I writing it this way? Why did I break it up? And why did I choose to put these two over each other? What's cosine of 3 pi over 2? What's sine of theta at 3 pi over 2? What's sine of 3 pi over 2? -1. It creates a 0 over 0. This we can just plug right into. We're good to go. So we have the limit is that's just 2 times a sine of 3 pi over 2 plus 1 over 2 times sine of 3 pi over 2 minus 1 times our limit, where we actually have our L'Hopital's issue. Sorry, this video is so long, but these problems are long. So over here, what is that? -1, -2, plus 1, that's -1. This is 2 times -1, so this is -3 times. Well, now let's do our L'Hopital. So we got a positive 1/3 times whatever the answer is here. So we're going to do our L'Hopital's. Limit is theta goes to 3 pi over 2 from the left. The derivative of cosine is negative sine. The derivative of sine is equal to cosine. So it looks like we ended up with the limit is theta tends towards 3 pi over 2 from the left of positive 1/3 times that negative. So negative 1/3 tangent of theta. So cool. Where does it go? 3 pi over 2. Does it go to infinity? Does it go to negative infinity? Where does it go? I'm going back to x's and y's. Tangents graphed like this. It's got issues at those 3 pi's over 2. And we're coming in from the left. I think that's going to infinity. Or negative infinity. Therefore, that means we have a vertical frickin' tangent line right there. But man, we didn't need to do any of that if we would have known that we were looking at the... Oh my goodness, where is it? It's way back here. If at 3 pi over 2, we just paid attention to the fact that there is a sharp edge and that thing is frickin' vertical. That's right in the crack. Oh my goodness. So we could find out that, oh, this does not belong up here. That doesn't belong up there. It belongs down here. Now, to do your actual problems, you would have to take these. You want to show the point where this works, you would have to take your pi over 6 and plug it back in all the way back up there. Sine of pi over 6 is 1/2, so 1 plus 1/2 would be 3 over 2 comma pi over 6. You got to plug in all your frickin' values to get the points. But don't worry, I'm not going to give you a bunch of stuff to make your life hell like that on tests, maybe on the homework. So it has been 17 minutes. I've got to shut the hell up. So once again, we found that there were 3 points where it was a horizontal tangent line, and we found out there was 3 points where the tangent line was vertical. Woo! Let's do areas next. See ya.